Okay, let's get started for this discussion. Welcome to this week's discussion, which is of the year 2023. So any questions so far about the course? Any questions you may have for one? Because today we'll be reviewing more about sequential logic. Let's get started. So last week we were seeing about this sequential logic, no? And we already reviewed this slide, but I'm just going to go quickly over them. So the difference between combinational and sequential is that sequential has a state that it takes into account also for the computation of whatever output it has, as opposed to a combinational logic that only operates over the current input. Then we have this design of a latch, this is an RS latch, and you can see that there's these feedback loops, no? So this way it takes into account whatever output, which is in fact the state, into the next computation of the input, no? Which will be result in the next state. No? And you can see the equation here. No? So really there's a difference between asynchronous and synchronous sequential circuits, in respect that the synchronous ones usually have a clock signal that lets them synchronize whatever outputs they have and whatever inputs they process, and they synchronize according to, you say, the rising edge of the clock. Where is mine? I cannot see this color. Okay, the rising edge, no? Now, how many states can one flip-flop represent? Well, usually it's it can only represent one bit, no? You say, and this bit can be two states, no? So in order to represent 2 to the S states, you need S flip-flops, or S flip-flop, no? And there are two types of finished state machines. The mealy ones that their output depends on both the next state. The output depends on the state, the current state, and the input. And the Moore ones, the output depends only on the current state. Yeah. And this diagram of the JK flip-flop. Again, in the flip-flops depend on a clock signal. So it's more or less the same as the RS latch, but well, there's some differences. But yeah, these flip-flops allows you to maintain the state given a certain the current state and the given input, no? And they also have this I'll say this feedback loop.
Wait, didn't S start a flip-flop or like
No, this is a JK flip-flop. Oh yeah, you see this?
Why is it called a flip-flop?
Because there's a clock signal that synchronizes all.
Or like that subset. Isn't that just, an SR latch?
This one?
Yeah.
Yeah, this is an SR, you see.
So why does it say a flip-flop?
Because you have this other part.
So like just extending that makes it okay. It's so, but like adding those two other AND gates makes it a JK flip-flop.
And you can see this state is not present in the SR latch. If you put 1 in the SR latch, it will output, I think, what will that? 0 0 or 1 1? I think 0 0. But in the JK, it toggles whatever value you have here. And again, it does this based on the clock signal. So by adding this, you can do this. And I don't know if the RS latch only depends on having NORs. I would need to check if having NANDs you can also use an RS latch, but yeah, it's basically. I don't know if that solves your question. Kind of.
I guess like my I'm just kind of wondering now, what's the difference between an SR flip-flop and a JK flip-flop?
No, but there's no SR flip-flop.
Yeah, because it says SR flip-flop right there on the slide.
Oh, yeah, right. But it's incorrect because it's a latch.
Yeah, okay.
Because the flip-flop is the entire thing. Because the flip-flop, again, depends on the clock sync. Yeah, hopefully that. Well, I guess, sometimes the terms are used exchange, like in exchange. So, well, yeah, the flip-flop is supposed to be used with a clock signal. And that's the reason. And while the JK flip-flop is characterized by this equation. So yeah. So yeah, this is the JK flip-flop. Then we also have the D flip-flop, where, as you can see here, the next state depends on what you have in both inputs, but in the D flip-flop, it only depends on the single input. And whatever you have in the D, it will pass it to the next state. Now, this may seem more simple than the JK, but in reality, the D flip-flop is usually composed of a JK flip-flop plus another gate. So, like, it doesn't necessarily is more simple than the JK flip-flop. And the thing is that we will also sometimes need this kind of equation to help us in whatever circuit we need, because as you can see here, the JK flip-flop already incorporates certain operations, no, in their output, whereas the D flip-flop is only the input. So sometimes this can help us with external logic to make it more simple, as opposed to the D flip-flop, which again only forwards the value that is in D. And we have the D flip-flop that when you have 0, it just maintains the current state. If you have 1, it toggles the current state, no? So those are all the types of flip-flop. I don't know if there's any other question with this. All right, well, let's go with the problems. So, first of all, we'll try some problems designing finite state machines. So let's see, no? A fair coin is tossed until 3 consecutive heads appear. Design a finite state machine to describe the process. So the first thing you need to, I guess, check when you're designing your finite state machines is what are our inputs and our outputs, no? So our inputs are the whether the coin was heads or tail, no? Heads or tail. And the output should be 1, 0 when this has thing happened, and 1 when 3 consecutive heads appear, no? So that's our 2 outputs we want. So the question is, if we were to design this finite state machine, how many states would we need? Well, also we need to choose what type of finite state machine to use, no? Like either the Moore machine or the Milling machine. I guess based on any of these, what would be the number of states we need to consider to be able to express this condition? So I don't know, any guess on this? How many states will we need to? Yeah, we need 4, no? Because, well, at least with the Moore machine. Yeah, maybe with a Milling machine. With a Moore machine, we don't need 4. We can try doing it with both. So let's start first with a Moore machine. With a Moore machine, we need 4 states. And let's call it your starting. Then you have your first head, a second head, and a third head. This with a Moore machine. And let's see, I guess with a milling machine, maybe we need just start. Let me just start. We may need start H. I think that's how would you do it with a milling. Well, let's see, no? I haven't tried it with a milling, but let's see. So you first put start. Let's do first the Moore machine. Moore. So we start here, and we know that in a Moore, the output is only a product of the state, no? You start here, and your output is 0, no? Because you haven't done anything. Then you have the first head, and it's still nothing, no? And you have this. So this would be, and just be careful, like this H is different from this H. This H is a state, while this H is an input. So just be careful with this too. So what happens if here we have a tails in the start? What should we do? What happens in the start state? We have a tails.
Go back.
Yeah. So we go back here. Also here, if after this H we got a tails, we go back. Oh. If we already have a heads and get another head, we go to this state, but it's still 0. We got a tails, well, we reset this, no? Because this only applies when we have 3 consecutive heads. We have 3 heads. Well, that's the ending condition. And yeah, no? If we have a tails, you can see. But what happens if we have a head here? What should we do? To this one? That's right. Yeah, that's the thing. No, this could be an ending state, so we wouldn't need to define this too. But I'm just to, I don't know. For this time, let's assume this is a cyclical game, no? So let's assume. But yeah, in reality, this should be the ending state, no? But
Is there a way that?
Yeah. Well, I guess the ending state is when you just leave it without any, I guess, of these transitions. Okay. So you cannot go anywhere else. So that's the ending state. Another thing, like, yeah, you can do this, but you can also think that you need to restart the count, no? So you need to go back to start and do all this again, no? So it depends, no? Again, the problem is indeed telling us that this is like the ending state, no? But just to, I don't know, continue this, we are doing it, no? But depends on what they tell you, no? Now let's try doing it with a milling machine. So I haven't done this, but let's see. So you have start. They have the first one, and they have the second one. So what you can do is, with heads, you output 0. Heads, you output 0. Tails, you output 0. Tails, you output 0. Tails, you output 0. And here, I don't think you can create this notion of an ending state, because here, for example, we need another head, but we need to point it to another state. Well, we could do a third state, but I guess if we want to do it like cyclically, we could just do this, no? It's 1 if we want to express it the same as here. So yeah, this would be the similar solution to this, but with only 3 states and with a milling machine. Does this make sense? Now, reducing the number of states doesn't mean that the circuit will be less complex. Usually with a Moore machine, you get more flip-flops, but less external logic circuits. While with a milling machine, you get less flip-flops, but a greater number of gates you need to use to incorporate whatever external logic you need to incorporate. So there are trade-offs. Huh? And only there's a conversion from an exact way of converting from milli and to Moore. I think you'll maybe see it in the lectures, but if not, I guess well, I didn't do any systematic way, but you can see that you can maybe try doing it something like this. So is there any question with this? All right. A little bit more of explaining the flip-flops. So this is a time diagram, no? And you can see that how it's affected by the clock and the other signals. So first of all, we raise the reset, and then we put it down. And at that point, you can say that the D input. So this is the D. And this is the Q. This is the not Q. And this is the clock signal, no? And there's a reset, no? Also some flip-flops have a reset, no? So you can see here, you put down the reset, and that's when you start playing with the inputs, no? You can see here that the D input is 1, the Q is 0, and the not Q is 1, and the clock is 0. So again, the flip-flops only work when you have a rising edge. So whatever you have in the rising edge, because this is 1, it will now put a 1 in the Q state, and in the not Q, it will put a 0. And because this always 1, even here, it will maintain the current state of Q as 1, because D is 1, no? As simple as that. I don't know if there's any question with this. That is just a time diagram, just to understand the dynamic behavior of the flip-flops. Because if it's clear, I don't know, who knows what does this circuit do? Can anyone guess what is this circuit doing? Flipping the value of Q, sorry? It's flipping the value of Q at sorry? At every rising edge, right? And what does this, I guess, what's the function it's doing by doing this? I don't know, do you know? Like by flipping the clock tick, well, flipping the value of Q at every clock tick, what is it accomplishing in reality? Do you know? Or anyone knows?
Like doubling the period of the clock, so it's kind of like creating a new clock that is rise every like twice, like half as often. Yeah, it's rising, doubling the period or decreasing by 2 the frequency. It's a frequency divider. So let's see. So yeah, no, we have. Let's see. No, we have D, we have Q, not Q. And we have the clock signal. No? So let's see, let's assume we have this clock signal. So let's assume first we have Q1 and not Q0.
And we have, well, D is equal to, sorry, D is equal to not Q, no? Because the way they are connected. So what will happen is that at this, because this is Q is 0, at this rising edge, Q will go to 0, and Q naught will go to 1. And this will stay like that until the next rising edge, when, because Q naught is 1, Q will go back to 1, Q naught will be lowered, and like that, no? And you can see, so it's a frequency divider because it's dividing the frequency by 2 of the clock signal, no? And yeah, you can see it here, no? This is the diagram, no? So and this is very helpful, no? Because, you know, sometimes you don't need a very fast clock signal. No, our computers have like this very fast processor with this very high frequency, no? But sometimes you don't really need that high frequency. For example, in you have ever played with Arduinos, no? And the button example, no? When you press a button, there's like oscillation, no? In a short time period, no? So if you had a very high sampling rate, at some point you would be getting 10 10 10. But by dividing by I'll say sampling for greater period with a greater period, or in that sense with lower frequency, you will get a more stable result than if you were sampling with a higher frequency. So that's one use of this divide by 2 counters. No, when you need a lower frequency in order to take into account this phenomena that at high frequencies operate, but at lower frequencies they are not present. Okay, any question with this? If not, let's go to this design problem. So now here we will do exactly the same, like get the finished state machine, but we also design the circuit. So let me see, design circuit that displays floor you are in. So it says, no? So let's say we have a building with 2 floors, main and second, and an elevator with 2 buttons, up and down. If you're on the main floor and press the up button, you go up. If you press it again, nothing happens. Of course, the down button takes you down if you're in the second floor. So let's see now. We have what are our inputs? Well, we have 2 buttons. So it's up, down. All right. What are our outputs? Main and second. So I guess anyone, what's the number of states we need in this case? And maybe with kind of finished state machine. How many states do we need to represent? Can anyone guess? Yeah. T states are equal to outputs, no? We are already doing that, no? So yeah, it's we can just use a more machine, no? All right. So let's see how, well, we have 2 states, which is main and second. So let's say that, let's put it all with respect to these labels. So when you're in main state, you have as an output main, no? And if you're in the second, you have as an output second. No? Later we'll put some values to that, no? Like a binary value, no? To represent that one. No? But let's just think it of as this right now. Okay, so we need transitions, no? And this happens when you go up, when you go down, and in the second floor, if you press up, you keep there, and you press down, you're here. So this is a state machine. No? Okay, now let's try building our circuit. And for that, we need to characterize this circuit with a truth table. More or less as we did it with the combinational logic. Although let's also I'll say put some numbers or encode it as binary with binary numbers, all this information. So let's say main is 0, second is 1, main is 0, second is 1. Let's say down is 0 and up is 1. So these are how we are representing all this information. And we need to create our truth table. So the way we'll be creating it is we have our current state, which let's call Q0n, current state. We have our input. Then we have the next state. And then we have our output. Next state. As you can see, it's only 1 bit in length because we can represent this information with a single bit. Although another way of representing it would be with one hot encoding, no? So we will need 2 bits to represent this, no? But it's more compact if you use binary representation. So we have this, no? And we can divide this into 2 groups. So this is the input. Like as input, we have the input and the current state. And as output, we have the next state and the output. No? So this can be maybe confusing, but that's how we should try dividing this. So we put all our combinations here. We put, and while we, based on this, we check our finished state machine and we see, no? So based on the current state, which is 0, which is main, and the input, if it's down, where are we going? Well, down. And our output will still be that we are in the main floor. No? If we are in the main floor and we get an up input, that means we are now in the second floor, and we have as an output 1, no? Because we are in the second floor. If we are in the second floor and get the down signal, that means we go down, and we get the main output. And if we are in the upper in the second floor and we get up, we will still be in the upper floor, and the output will still be that we're in the second floor. So yeah, this truth table is very easy, no? Okay, now we have this. Also, so this is a way of like describing this behavior, but you also find this this table can also be expressed the following way. You have, for example, Q0 and input, and you have Q0 and but you have no, wait. So the way it's expressed is, in fact, you have your current state, you have your next state. Well, in this current next state, it's also dependent on the input, and you put something like this, no? Input 0, input 1, and the output. So basically you just fill this table more or less similar to this. For example, we got here 0. So if well, it will be only 2 rows here, but we have 2 columns here. So if current state is 0, what will be next state if our input is 0? Well, it's 0. If our input is 1, no? We are in state 1, which is the second floor. What happens if we are 0, 1, no? And the output is the output is the same as this, no? So what would it? I don't know if you put also 2 columns here. Well, in this case, no, because the output is based on a Moore machine, so the output only depends on the next state. But the next state is modified by this. So yeah, you would need to do something like this, I guess. But yeah, I guess this is another way you find it expressed. Well, let's stick with this version right now because it's a little bit more easy to see, and it's more based on your combinational problems. All right, so let's see how. Okay, so now let's relate it with the inputs with each of the outputs, no? And for this, so you know, like, yeah, you have your flip-flop that determines your state, but you also need some external logic to determine when to transition to another state, and that the flip-flop itself cannot provide. Well, depends on which flip-flop, no? Right now we are going to use a D flip-flop because it's right now the most simple theoretically to use. Although I already told you that the implementation is not necessarily simple. So you also need to define which kind of flip-flop you're using. And again, we are using the D flip-flop. So that means that the Q0 and plus 1, which is the next state, will be defined by D. No? That this way we will be maintaining this state. No? Obviously, if we had a JK flip-flop, we would need to put the equation here, no, of JK. And we will need to, I guess, have the table of JK flip-flop to see how it corresponds to this single bit input, no? All right, so we have this relation. So based on this, we need to relate whatever we get as input, well, whatever is our next state with whatever we get as an input, no? And for this, we will try doing a Carnot map to just get the simple representation, because we can see, you can interpret this as a truth table that we need to simplify, no? Where we have our mean terms here based on our input. So let's try doing that. We have 2 inputs and 1 output. So let's try doing create the Carnot map here. Okay, let's see, Q0 and input. We have 0, 1, 0, 1. We have 0, 1, 2, 3. And this will be for the next state case, no? But we also need one of these for the output, no? So let's copy this table. Let's put it here. No? This one is for the output. So again, we need to relate the inputs with both outputs, which is the next state and the real output. We need to check the mean terms. So it's in 1 and 3. 1 and 3. And the rest are 0. No? And what does the output say? 1 and 3. So it's exactly the same, no? So we don't need really two Carnot maps. With a single one, we can already get the equation that characterizes both outputs. We just do this, no? We get that the next state is a function only of the input. And you can see that the output is also only dependent on the input. So that's it, no? That we need to have a circuit that expresses this relation. So how would you create a circuit that does this? Like, any guess? We need to have a circuit that does this. And let's say we have, I'm going to help you. So let's say we have input, our input signal. We have our output signal. We have our clock signal. So how do we do this? What do we need here? What do we, anyone? How do we build this circuit? Yes. Basically, that's what this equation is telling us. Because we know from this other equation that Q0 next state is equal to D0. And if you remember what a D flop is, there's this D, which is the D0, this is the Q0. So this means that whatever we get here, we will get it, you say here, no? Like this is the same as here, no? I'm just going to remove this. And because D0 is equal to the next state, then we should just put it equal to the input. No? We just connect here. And because the input is equal to the output, we just connect this. And we also have the clock signal here. And yeah, that's your circuit. We had to do all this only to get just connecting one flip-flop directly to an input and output. Hopefully you won't have to waste your time doing this. You'll figure it out whenever you find something like this. Any questions with this? And you can also use logisim, no? You can see here. This is our D flip-flop, clock signal, output. If we have 0 and we press the clock signal, well, it will maintain 0, no? If we put 1, after one clock cycle, it will be 1. We put it 0. So that's how it should work, no? Any question with this? The flip-flop, you get it from the memory, and the clock, you get it from the wiring part. And these are your this. That's how you build this circuit. All right. So now let's go with a more challenging problem. So this is telling us to build also a sequential logic circuit, but now does this, no? To output a 1 when the circuit sees a 1 0 1 0. Otherwise, output a 0. So let's see how it works. This is our input and our output. You get your first 0 as an input. You output 0, 0 0, 1 0, 1 0, 0 0, 1 0. But when you get this sequence, you'll get a 1. Then you continue 1 0. But then you get a 1 again because now it's considering this other sequence. And then it goes like this, no? So you can have this kind of I'll say detections, no? When you need separate 4 bits that are 1 0 1 0, you can borrow 2 of the bits that was used in another similar sequence, no? Okay, so what are our outputs? 0, 1, and our inputs 0, 1, no? So can anyone guess how many states do we need? And which finite state machine to use? No? Mhm.
You could, I think, if you four states
With which finite state machine?
with. Would it be a Moore machine because it's all offset by one?
It would be with a milli. With a more, I think 5, but with a milli you would get like 4, I think. Well, 4. Yeah, no, that's a fact. No? But yeah, with a more you may get 5. I haven't done it with a more, but I think that would be. But yeah, that's right. No. Yeah, well, I guess I'm not sure with a more, but I know with a milli it's 4 states. So yeah, let's just start this time with a milli machine. Okay, so states, we have our states are the start. Then when we get a 1, when we get a 1, 0, and when we get a 1, 0, 1, and we'll see how this works. So we have our start state. We have our 1. We have our 1, 0. And we have our 1, 0, 1. Okay, so if you're in the start and you get a 0, well, you output 0 also, no? So you get back to the start. Then you transition to 1. Only if you get a 1 here, no? But you still output a 0. Then if we are here, you'll get to this next state if you have a 0, but you still output a 0. Then you'll go to this state if you get a 1, although you'll still output a 0. And here is where it may start getting challenging, but let's review what happens here. If we're in a 1, well, now let's assume here. So if we get a 0 here, that means we would output a 1, but where should we connect this to have this behavior? Again, if we get a 0 here, that means we are detecting this sequence and we should output a 1, but where should we connect this state to which other state in order to continue detecting these patterns? Anyone guess?
One.
No, yeah, I guess so you have a 0 here and you'll output a 1, but we need to connect this state to another state, no? Exactly. Because that way we can restart detecting this pattern, but thinking that we already have these 2 bits borrowed from the previous pattern. No? That way you can get this behavior. And you can see it this way, no? For example, let's assume we have 0, 1, 0, 1, 0, 1, 0. So you are here. You're in start. Then you get a 1, so you're in number 1. Then you get the 0 and you are in 1, 0. And then you get a 1 and you are in 1, 0, 1. And then you get a 0 and you're in 1, 0, but you output a 1 here. And then you get a 1 and you're in 1, 0, 1. And then you get another 0 and you're back to 1, 0, but you output a 1, no? And that's how it should work. Now let's see what happens if we have here, well, we have a 1 here. What happens if we have a 0? Well, the transition. What happens if we have a 1 here? Well, we go back here, no? Because a 1, if we are here, for example, and we have another 1, like we are still in this case because at least we have a 1, no? It's not that we need to go back to the start because we have the first bit of the pattern. Okay, here we only transition when you get a 1, but if we get a 0, you don't need to go back to the starting point because then, yeah, there's no pattern there, no? So you need to go back to the beginning. This is when you get a 0. And finally here, if you get a 1, you need to get back to the state that is here. Because at least you now have a 1, no? And you can keep trying to see the other bits. Yeah, maybe, yeah. Like the labels of the states are however you like. I just put it like that, but yeah, that could be a good label to replace it. Any other question? Like this is the state machine, the milli state machine. I think these are all the possible cases, no? 1, 2, 1, 2, 1, 2, 1, 2. Yeah. Because now we need to build the circuit based on this. So what we can do here is another truth table. But now let's see, no? So we need to choose how to represent these states. And we can do it with a binary number of 2 bits in length, no? Because we have 4 states, no? So we can assume start is 0, 0, then 0, 1, 1, 0, and 1, 1. No? So you can use 2 states, which means we need now 2 flip-flops. Because each flip-flop can only represent 1 bit. So we have now Q1N, Q0N. This is our current state. Then we have our input. Then we have Q1N plus 1, Q0N plus 1, and we have our output. So these are the next state, no? Again, because our state is now composed of 2 bits, so that's why we need 2 Qs. And the ones in the left are all our inputs, which consist of the true input and the current states. And the ones in the right are our outputs and the next state. So we need to relate all these together, no? So first we can just put all the combinations here, no? It will be 8 combinations. 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1. And we can see how these relate to the state. So let's see. So you can see that this is the start state. This is the 1 state. This is the 1, 0 state. And this is the 1, 0, 1 state. And based on the input we get on this state, we should go to another state. So based on our diagram here, let's start filling out this table. So if you're in the starting state and you get an input 0, well, you are still in the starting states and you output a 0. Well, let's just do the states, the next state outputs first, and then we'll do the outputs, the true output state. Output values. We are in the state start, which is state 0, and we have a 1, we'll proceed to the next state, which is the state 1. No? If we are in state 1 and we get a 0, that means we go to state 1, 0, which is state 2. If we get a 1, we stay in the same state, which is 0, 1. Now we're in state 2, which is 1, 0. And we have a 1, we proceed to the next state, which is state number 3, which is state 1, 0, 1. And if we get a 0 here, we go back to the start, which is state 0. And if we are in state 3 and we have a 0, we go back to state 2. And if we have a 1, we go back to the state number 1. And let's see all our outputs. There's only one case when we have a 1. And this is when we go from the state 1, 0, 1 to and we get a 0, no? So this would be when we get a 1. The rest are zeros. Yeah, no? Yeah. All right. So now it's again, just to simplify our lives right now, we can choose to use a D flip-flop, which means we only care of one of we need 2 flip-flops, in fact. And the relations between the flip-flops and the next state is the following. So Qn plus 1 will be equal to D1, and Q0 and plus 1 will be equal to D0. Again, if we use JK flip-flops, we will need to somehow change this input into something that we will have this equation that relates the 2 inputs of the flip-flop with the current input, no? So it will be a little bit more complex in respect to the truth table, but you can still use it. And in fact, because the JK flip-flop is an OR of product terms, we can also use that logic to help us simplify the entire logic of that is displayed in this truth table. But because we don't have that, let's just stick with the D flip-flop. So now we have 3 outputs, so we need 3 different Carnot maps to simplify the circuit. So let's have here our 3 Carnot maps that depend on this input, which is Q1 and Q0 and input. And this is 0, 0, 0, 1, 1, 1, 1, 0, and this is 0, 1. So let's enumerate it. 0, 1, 3, 2, 4, 5, 7, 6. And let's see. So we check the midterms here. Oh, okay. We need 3 of these, no? For each of the outputs. We put it here. I think we need no. Whenever, let's do this again. Okay, so this table will be for the Q1 and plus 1. Oh, no. Oh, Q1 n plus 1. The next state of the first bit of our state. This will be for the second bit, least significant bit of our next state. And this should be for our output. Okay, so let's go with the first column. We see that the midterms are in 2. Okay, in 2. In 5 and in 6, no? 5 and 6. The rest are zeros. For the second case, it's in 1, 3, 5, 7. 1, 3, 5, 7. And in the third case, well, there's only 1 in 6. So in this case, we don't really need a Carnot map. Well, if we go with midterms, with maxterms, maybe you can do something here, but let's just stick with the midterms. All right, so now let's proceed with how we solve these Carnot maps. We have here 1, another here. We have for the 4 here. We have 1 here. All right, so let's get our expressions. So we have here that Qn plus 1 is equal to, but we already know that it's this one. This is equal to Q0 and not input, or Q1n and not Q0n and input. Yeah, no? Let me just check. Q0 and not input. Q1 and not Q0 and input. Yeah. Okay. For this one, we have that Q0 n plus 1, which is equal to D0, is equal to the input. So this is very simple. And for this one, we have that our output, it's equal to Q1n and Q0n and not input. So okay, we already have all the equations. So now it's just a matter of designing it. And for this, let's just use logisim to try doing this thing. So we need 2 flip-flops. This is the let's call it D1. And this other would be D0. And we have a single output. This is our output. Out 0, I guess. And our input. So let's say in 0. So those are our inputs, outputs, flip-flops. But now we need to connect them. And this is where these equations come into place, no? So at least we can see that the D0 is equal to input. So we just connect this with this, no? So that's it for this the flip-flop. Now, what does the D1 is connected to? Well, this is a little bit more difficult. So it relies on one AND gate of 2 inputs, or one AND gate with 3 inputs and an OR gate, no? So we have here, we go to gates. The gates. And one AND gate here. Another AND gate, this time of 3 inputs. And we need an OR gate here. And oh yeah, well, yeah. So and well, we also need a. How do I do this? How can I move here? Huh. Oh. And I need a NOT gate for the input. All right, let's move this to here. Move this. Well, let's just wait. So we have one of the inputs to this AND gate is a negated input, so that's why we just connect this to the OR gate, and this OR gate to this D1 flip-flop. And we see it's and Q0 are not input. So this is a difficult one. Q0. No? Yeah, no. Go. Shouldn't. Yeah, Q0 and not input, okay. No, but this is not Q0, this is, sorry. Q0. Okay. Q0 and not input. So that's what we have here. And then Q1, not Q0, and input. Q1. So this is the thing. Q1. No, well, not Q0, but because the flip-flop already provide a negated state, so you can use this one. It's just a matter of connecting it. And the inputs. Let's see. Okay. And okay, we have this. This is the logic that is behind the next state of the most significant bit of our state. And finally, our output, which is an AND of 3 inputs. So output. It's an AND gate of 3. And this is connected to here. And it's what is Q1, Q0, and not input. Q1, Q0, and not input. So yeah, maybe you can draw it nicer than what I'm doing here. Okay, so now we should test it, no? If it's how it should work, no? We need our clock signal. All the don't forget about that. Our clock signal. that is used for these two. No, what's happening? Yeah, okay. Hopefully it's connected correctly. So let's see, we have 0. Okay. We have a 1. Wait, okay. We have a 1 for one cycle. We have a 0 for one cycle. We have a 1 for one cycle. And we have a 0 for one cycle. No, well, I think, well, you had a 1 there at one point, no? Okay, well, you see, that it's detecting it, but I think, I don't know what's happening with the clock. Maybe I'm not doing correctly, but you can see, that at some point it's, okay, we have a 1 there, which is because we have 1 0 1 0. But what happens if we just maintain the 0 there? Well, now you don't get a 1. So yeah, this circuit works. So this is sequential logic for you. Any question with this? Now you can also try building it with your real circuits, with your you can buy some of these integrated circuits and try doing it. For example, we have already here some. You would just need your breadboard and connect these inputs to whatever you need. Like these chips, you can actually buy them, so you could try doing it. If not, it's okay. So yeah, that's the solution for this problem. And finally, there's a last question, which you can see is a lot more complex. Maybe the size of the problem statement correlates with the complexity of the circuit. So let's say, so consider a finite state machine that controls the seat belts and no electronic signs for a commercial airline. The state machine has 3 inputs, alt 10K, alt 25K, and smooth. Whenever the airplane passes 10K or 25K feet, moving in either direction, alt 10K or alt 25K respectively, will pulse high for one cycle. If the plane is not climbing, descending, or experiencing turbulence, the smooth signal will be set to high. The state machine should set the no electronic sign to high when the plane is below 10K feet and low otherwise. The seatbelt signal should only be low when the plane is above 25K feet and smooth has been asserted for at least 3 cycles. Assume that the plane is initially on the ground, and using a one-hot state encoding, derive the logic needed to compute the next state and output logic of your state diagram. So that's a lot of information. So let's see how we should proceed. Again, always remember about what our outputs and our inputs. No? So our outputs in this case are the seatbelt and no electronic signs. No? Seatbelt and no electronics. All right. Our inputs are, you can say there's 3 inputs. Well, it's already telling us, no? Alt 10K, alt 25K, and smooth. And smooth. Although we can also consider that none of them appear, no? Because the input only happens for one cycle. But otherwise, there's no signal, so it's none, no? So now let's try seeing the relationship with the inputs and the outputs. So it's telling us that when the airplane passes 10K, so it starts at the ground, no? Well, sorry. So when the plane is greater than 10K, the input will be alt 10K. It will signal alt 10K, no? Input. If it's greater than 25K, the input will be alt 25K. Well, and this is when, I guess, not only when it's greater, but also when rising or descending this at this altitude, no? So this is plus minus, I don't know. Maybe we should express it like that. So it will activate this input when it ascends 10K or when it ascends 10K, and when it ascends 25K or it ascends 25K. And when it's like smooth, I don't know, whenever so when it's not climbing, descending, or experiencing turbulence, you have your smooth, no? Say when it's stable, which I think is a synonym for smooth. So now what's the relationship with our outputs? Well, when it's at lower than 10K, sorry, not equal, lower than 10K, our output will be that let's abbreviate this with seatbelt and NE. So our seatbelt signal and our no electronic sign will be up, while we will be displayed. But when it's greater than 10K and lower than 25K, she said too high when the plane is below and no others. Yeah, the no electronic sign will be now low, no? But the seatbelt will be on. And only when the plane is at an altitude higher than 25K and the smooth signal has been asserted for 3 cycles, like you say 3 by smooth. So we have not seatbelt and not electronics. So those are the relationship between inputs, outputs, and whatever conditions we have. No? So it's telling us initially on the ground, no? So let's start building this truth table. Well, sorry, this state diagram. We're in the ground. I guess, how many states do you think we will need for this problem? Based on all this information. Anyone guess? Like any estimate on how many states do we need and with which state machine? Uh-huh. 5 with a million? Yeah, maybe. More with a more we need 6. So yeah, it can be 5 with a million. Let's just with this for this problem, let's start with let's just use a more. But yeah, you can also do it with milli, but yeah, let's just start with a more right now. So yeah, you need 5 states, no? And let's see which states are those, no? So states. So we start at the ground. Let me just start at ground. Then you need to know when you're at 10K. You need to know when you're at alt 25K. And then you need to, when you are at the 25K, you need to wait 3 cycles, no? So we need three like smooth states if we're in a more machine, no? So it's 1, 2, 3 plus other 3, so it's 6, no? And let's see how do we draw this Moore machine. So it's Alt 10K, Alt 25K. We have smooth number 1. We have smooth number 2. And we have smooth number 3. Let's just check which outputs we have in each of these states. So if it's at ground, it's you have the seatbelt and no electronics sign on. But if you now are in Alt 10K, you have the seatbelt, but not the no electronic sign. In the Alt K, it's the same. And in the following, it's the same, except for the last one where you now deactivate the seatbelt and you have deactivated the no electronic sign. Now it's time to figure out the connections between all these states. So if you're in ground, if you receive, what are our inputs? If you receive the smooth or known signal, like that means we're still in the ground, no? Known or smooth. Or well, we are maybe not at the ground, but flying at an altitude that is lower than 10K. Only when we get the Alt 10K signal do we transition to this one. Furthermore, when we transition from here to here, only when you get the Alt 25K. Then we transition from here to here if we get a smooth signal. And we transition to here again if we had a smooth signal. And again, if we have a smooth signal. And here we go back to ground if we get the Alt 10K. Because if you remember, Alt 10K is activated when you climb or descend 10K altitude, no? The same with this. You go back here if what happens if you don't receive any signal? Because if you don't receive any signal, that means you're also not smooth. So you go back here if you okay. Let's see, let's draw it from here. So no signal. And the same with this, no? You need to repeat again, wait for 3 smooth signals, and then you may deactivate the seatbelt signal. But what happens, but also during these states, you are in the Alt 25K, and you can also receive the Alt 25K, no? Which means you're somehow descending, no? So in that case, you would go back to here. You receive the Alt 25K. And the Alt 25K. Now, if you receive another smooth signal here, you stay here. If you receive no signal here, you stay here. Well, no or smooth, no? Or smooth. And I think that will be it for this state diagram. I think we have considered. Obviously, there are some combinations that we are not considering. For example, in the ground, we are not considering if we receive the alt 25K because that's not supposed to happen. Although if we wanted to design a very robust controller, we would need to somehow incorporate the possibility of receiving the alt 25K and interpreting it as maybe as you say a malfunction or something like that, no? Or whatever you are told to interpret it as. Okay, we have this, and now we should traduce it into a truth table. No? But first of all, we need to see how can we encode all this information, because they are telling us that we should use one hot encoding. Well, one hot state encoding. No? So then that means that for each possible output, we will have 1 bit. So seatbelt will have 1 bit, no electronics will have 1 bit. And therefore, while we could maybe encode this with a single bit, because we're using one hot state, we're using 2 bits to express output. To express input, we are using 3 bits, 1 for each possible condition, 1 for alt 10K, 1 for alt 25K, and 1 for smooth. And if there's no, for example, alt 10K would be represented with 100, alt 25K with 101, 1010, smooth with 001, and none with 000. No? You can see that we could represent all this information with only 2 bits, but because we are using one hot state encoding, we are using this notation. In this case, we are using 2 bits, so it's seatbelt, no electronics, and obviously, if there's no signal, you can use 0. And there's also a combination from here. So yeah, well, in the case of the outputs, you don't have one hot state encoding. You only have 2 bits, but yeah, for the inputs, you can. It's only one hot state encoding because you only have a 1 and zeros. No, like there's never a possibility of having more than 1 in this vector. Or for the output, you can have that. No, so output is not one hot state encoding. And now the states are also one hot state encoding, and because we have 6 states, that means we have a state vector that is 6 bits in length. So for example, let's see, for the ground, we would have something like 0, 0, 0, 0, 0, 1. For the alt 10K, we have 0, 0, 0, 0, 1, 0. Alt 25K, we have 0, 0, 0, 1, 0, 0, and like that, no? And that is because they are telling us to use one hot encoding, no? We could use binary, but that's not what they're telling us, no? So based on this, the first thing would be to use a truth table. Although in this case, we won't do the truth table we were doing before because we will have like a lot of columns and rows, no? Because now we're using 6 bits to represent the state. So, and in fact, not all combinations are being used, so we don't need to do that. The way we are going to build our state will be the following way. Our truth table will be the following way. We put here the we can say we put the combinations of our states. No, we have 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. And wait, this corresponds to ground. Alt 10K, Alt 25K, smooth 1, smooth 2, smooth 3. Those are all our states, no? So we have
If it's easier to do it binary, why don't we just use a decoder and then make a truth table? Can we do that as well?
Use decode and encoder, right? Yeah. Yeah, I guess, but yeah, we could do that. Yeah, we can do that. But I guess just for the sake of this example, let's do it. But yeah, you could do that. That will be more intelligent. Yeah, certainly. So yeah, no, these are all our I'll say our state, and we will have 6 flip-flops, no? So maybe not the best. Well, we will have 6 flip-flops if we express it using one hot encoding, or no, we don't. Okay, yeah, just because we are expressing it this way, no? Wait, 6. No, sorry, that's not the notation. 5, 4, 3, 2, 1. So you have your inputs, which is I'll say alt 10K, alt 10K, which is 100. If we remember, we have alt 25K, which is 010, smooth, which is 001, and known. Well, I'm not going to have space here. Unknown, which is 000. And we have as our outputs the not electronics and SB, no? So these are our outputs. Inputs. And yeah, like we will have like a reduced ground truth table. We're not going to put all the combinations because not all combinations are necessary here. Only this. We have here. Okay. So in this case, so if you're in this, you're sorry. No, okay. No. Yeah, sorry, I forgot that column here. If you're here and if you're in the ground and receive this signal, you'll go to alt 10K. If you are here and receive you're in the alt 10K and you receive ground, and you receive alt 10K, you go to ground. Then if you are in alt 10K and receive I'll say the alt 20K, you go to alt 20K. Let me just fill all these because don't have that much time. Okay. 25K, 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 25K. You have here, you go to smooth 1, smooth 2, smooth 3, smooth 3. And you go to Alt 10K, Alt 10K, Alt 10K, Alt 10K. And I think that will be our table. The other combinations are not possible. And just as our outputs, we will get 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0. So this is like another way of representing, no, the truth table. These are our next states. So you say next states, next states. Well, the ones in orange, and these are our outputs. So we have this, and the way of finding the equations. Now we can just think of, for example, for next state, for ground, for example, how ground is characterized. Well, we can see, no, the ones that have ground here. So it will be, and let's assume, well, for example, for ground, we will have that you go to ground when you are in state 1, well, in Alt 10K, and you receive, okay, so let me just, and you receive the Alt 10K input, no? Okay, this may not be the best way of expressing it. Like this is the Alt 10K state, and this is the Alt 10K input. So you are in ground if you are in the Alt K state and you receive the Alt K input, no? But not only that happen, no? Or where you're in ground and you receive and if you receive the known signal, the known signal, or the smooth signal, no? Which in the inverse logic would mean that when we don't receive the Alt 10K signal, no? And not Alt 10K. So that will be again, this is the state, and this is the input, no? And we are using inverse logic because the ground state will still be in the ground if you don't receive the signal, no? The Alt 25K, you cannot receive it, so we don't take that into account. And you only receive when it's smooth or none. But we apply inverse logic, so it's when you don't receive the Alt 10K input, no? And you can go with each of these next states. Like this is the next state. How do you go to this ground if you're in this in whatever state you are, no? So you can build all these equations, and then you can do it with the output, no? And then you will build your circuit, but we won't do this because it's a lot of things to do. But in the solutions for these slides, you'll see that, well, even in there, they don't build a circuit, but you'll see all the equations, no? So I think that will be it for today. I guess any question with this? If not, I'll just give you the tenant form.
Are we doing it in like IEEE format stuff like
No, it's just
like the standard like,
0 point something.
yeah, that.